Hi, everyone. Thank you for joining in. I'm here to present our paper, Designing Fairly Fair Classifiers via Economic Fairness Notions. This is a joint work between me, Safwan Hossain, Andjela Mladenovic, and Nisarg Shah, and we're all at the University of Toronto. Our work is largely centered around fairness for machine learning algorithms. And as ML and data-driven algorithms are applied in ever more socially sensitive settings, for example, granting bank loans, granting parole, or targeted advertising, fairness becomes an imperative question to ponder. And this was largely due to algorithms being data dependent, and the data may have significant bias. And naive solutions like ignoring sensitive attributes are simply not enough, as other attributes in your feature vector may contain enough information to recreate that bias. Moreover, we may often want to design algorithms that address specific social inequities. Due to this, there's been a large yet nascent interest in studying fairness in a machine learning context. On the other hand, however, fairness has been studied in economics for over 100 years in the context of fair resource allocation. Two popular concepts to arise from this are envy-free and equitability. Now, these are both utilitarian notions, and they both assume the existence of a utility function mapping outcomes to agent preferences. So envy-free states that no individual should envy another. Basically, the utility an individual has for their outcome is higher than the utility they would have for the outcome given to any other individual, and this should hold across all individuals. Equitability simply states that individuals should receive roughly equal utility. So basically, the utility I have for the allocation given to me should be roughly equal to the utility someone else has for the allocation given to them. So within a machine learning context, prior works on fairness have largely focused on binary decision problems, where there's a very clear notion of good or bad. For example, everyone wants to get a loan, everyone wants to get parole and leave prison. In many scenarios, however, the individuals in question may have a heterogeneous preference over the various classes. For example, we can think about targeted advertising, where individuals may have preferences over the different ads. Or even in the bank loan settings, there could be a number of different loans that we may want to choose over, and that depends on the kind of person we are. And existing fairness notions simply don't work well in such settings. They weren't really designed for them. However, economic fairness notions are fundamentally based around utilities, which are apt to address this because utilities quantify individual preferences for different classes. However, envy-free and equitability, as stated in the economics literature, is just far too stringent a constraint in the machine learning setting, because envy-freeness is essentially applied pairwise across all individuals, and in a machine learning setting, this would be over the entire training set, which is a bit expensive. And moreover, such fine-grained fairness across every single individual may not necessarily be needed, as group-based notions of fairness are really what we're going after in machine learning, and that's where most of the popular fairness definitions are coming from. Our main contribution in this paper is to propose novel relaxations of envy-freeness and equitability in the style of classical group fairness notions in machine learning. Our proposed notions are quite general, and they capture several prior fairness notions, such as statistical parity, equalized odds, equalized opportunity as special cases. Moreover, our notion is built from the ground up for a multi-class setting, and as such, it provides a natural multi-class extension to these ideas, which were originally designed and written out for binary classification settings. In our work, we explore our fairness metrics from a packed learning perspective and provide generalization error bounds using radiometric complexity. And due to the generality of our notions, these bounds apply to the prior notions mentioned as well. Lastly, we experimentally assess our fairness notions and provide practical implementation strategies and takeaways. So as mentioned, fairness has been a hot button topic of study in research for the last few years. And there's kind of two main threads in this. There's individual fairness and group fairness. So individual fairness attempts to ensure fairness with respect to individuals. So some examples of this could include fairness through awareness, which is the original paper that started this field a few years ago, which argues that similar individuals should be treated similarly. However, one of the main caveats of this notion is that it assumes the existence of a pertinent similarity metric for every task, which is often not realistic. There's also application of individual NV-free, or the classical NV-free notion for machine learning, which was done a couple years ago. But as we argued, we believe that this is far too stringent for machine learning. But on the whole, individual fairness tries to achieve fairness across every individual in the training set, or approximately so. Group fairness notions, on the other hand, attempt to ensure fairness across sensitive groups. So that could be race, that could be gender, that could be age groups, and so on and so forth. So some common notions include demographic parity, equalized odds, equalized opportunity. So for example, demographic parity argues that the probability of getting a positive class is the same irrespective of group identity. So regardless if you're black or white or male or female. Equalized odds argues for something similar. It is that we now condition not only on group identity, but also on the ground truth. So the probability of getting a positive class is irrespective of your sensitive attributes, given that you are true ground positive. And equalized opportunity is something similar. However, we note that these group-based notions are largely defined for binary classification setting, where there's again a commonly understood notion of good, and the preferences are homogeneous. But what if there are more than two classes? What if individuals have different preferences? And many real-world examples and instances are actually in this more muddled domain. I'll now briefly discuss our model to make things a bit clearer as we proceed. So largely for notational ease, to capture settings where there is a ground truth and there isn't. For example, in target advertising, there is no real ground truth. However, in bank loan settings, there is a ground truth. So to capture settings that are across both of these, we denote an extended feature vectors, which includes the feature vector for an individual along with possible side information such as ground truth. Note obviously that the classifier itself does not have access to this extended feature vector. We encode our individual preferences in a utility function, as is done in classical economics literature. We don't make any assumptions about the utility function, except just for normalization purposes, we assume that the utility is mapped to a number between 0 and 1. In our work our work is largely based on group fairness. We define groups to be simply a collection of individuals, and we don't make any assumption based on this. And group NV freeness and equitability are applied between two groups in our work and not between individuals. So this cursive G represents the set of pairs on which we desire to apply fairness to, because as we mentioned, NV freeness and equitability are both pairwise notions. So here cursive G represents the pair of groups that we wish to apply fairness to. And note that this framework allows a lot of flexibility. First of all, we don't make any assumption about group identity. For example, groups need not be mutually exclusive. And moreover, we don't need the fairness to be applied symmetrically. For example, cursive G could include specific groups that we want, specific pairs that we want fairness to, and ignore others. So this allows for a really general framework. And lastly, our goal is to seek a multi-class randomized classifier that minimizes the loss while also being subject to fairness constraints over this cursive G. So we denote our notions, group NV-free and group equitability. So informally, let's say we have two groups, G and G hat. So group G is group NV-free of group G hat if the average utility individuals in group G receive for its class is higher than what they would receive on average if given the classes prescribed to those in group G hat. So basically, group G on average does not envy group G hat. So again, this is applying NV freeness across groups and not individuals. Similarly, group equitability between groups G and G hat ensure that the average utility individuals in group G receive for their class is equal to the average utility individuals in group G hat receive for their class. So just a quick side note, NV-free and group NV-free are not symmetric constraints. So NV-freeness between two individuals or two groups does not, so between groups G and G hat does not imply NV-freeness between G hat and G, whereas equitability is indeed a symmetric concept. But you can choose exactly how to apply this using the cursive G that we mentioned here, which states exactly what pairs of groups that you're going to apply this constraint to. So roughly group equitability is saying that on average, the utility received by one group is equal to the utility received by another group. So note that individuals still have their own utility function. So individual utility functions are still maintained. It's just that we are not equalizing or ensuring fairness across individuals, but across groups. So we say a classifier is group NV free or group equitable if it is so for every group pair that is listed in this cursive G, so as we mentioned. And lastly, again, we make no assumptions about G or G hat. So now we come to some of the technical results of our paper. So one of the key advantages of our notion that we realize is that it's quite general. So what this theorem informally states is that by appropriately setting utilities and defining the group set, demographic parity, equalized odds, equalized opportunities, equalized financial impact, all of the a lot of the group fairness notions that have been proposed in the past can be shown to be equal to group NV free and group equitability. For example, using 0-1 utilities and defining groups based on sensitive attributes and ground truth, we can recover equalized odds. And you can show a similar strategy for the rest. So this illustrates that our notions are quite general and encompass a number of existing ideas. And moreover, as our notions apply to multi-class settings, and group NV free and group equitability can be viewed as natural extensions of these prior notions beyond the binary classification setting. So this theorem is largely targeted at an interesting theorem that was mentioned in the original equalized odds paper, where the authors show that there exists a procedure whereby they can take the output of an ERM classifier and the sensitive attribute. So they don't need access to the underlying feature vectors, just the ERM classifier output and the sensitive attribute. And they can post-process it to ensure that the final classifier satisfies the equalized odds. So this is in general quite desirable because you don't need access to, you can essentially post-process fairness. However, our theorem in here informally shows that in the more general framework, without access to utilities, post-processing is generally something that won't lead to anything that is substantial. So the post-processing fairness generally leads to a very extremely restrictive set of classifiers in the group NV free and group equitability setting. And indeed, this is not that surprising given that our preference-based notions of fairness crucially need access to the utilities. And without such access, we can't design any robust sort of classifiers, and we can only rely on very restricted set. So one of the key questions we wish to ask in our paper was whether fairness can be learned. And more technically, we want to study fairness from a pack learning perspective. So the pack learning goal is to show that the results in the unseen population approximately matches those on the training set with high probability. And indeed, in the machine learning theory community, this is generally done for loss function to show that minimizing training loss will also lead to minimizing test loss. However, we wish to apply this to the fairness domain. That is, can we ensure that the unfairness in the test set or population is no more than epsilon higher than the empirical unfairness in the training set with high probability, let's say 1 minus delta. So our key generalization theorem states that given an epsilon and delta, our generalization theorem outlines the sample complexity required to ensure that the training and test unfairness is within epsilon with probability 1 minus delta. And generally, this sample complexity is scaled logarithmically with G, but we'll come to that soon. So this theorem is largely proven using the Rademacher complexity framework. And although the proof is a bit tedious and quite technical, the main challenge in this theorem stems from having to remove the dependency on the sample complexity, like having to remove the dependency on the utility function and the groups in G, because again, we made no assumption about the utility functions or the groups. So, and they can be arbitrary. So removing this dependency was the main challenge in this theorem. So some quick takeaways from our generalization result. Firstly, as I mentioned briefly earlier, sample complexity scales logarithmically with the number of pairs of groups over which fairness is desired. So it scales logarithmically with the cursive G set. And this implies that even with an exponentially large set of groups, or a set of group pairs over which we wish to apply fairness to, sample complexity will still scale polynomially. In other words, we allow for exponential number of groups while allowing good generalization bounds. And just a quick note that this generalization result extends to prior notions like DP, EO, and others, again, because of the generality of our framework and NV freeness and equitability, group NV freeness and group equitability encompassing those ideas. In our last theoretical result, we wish to briefly analyze the worst case trade-off between loss minimization and fairness. So simply put, how unfair could the ERM solution be in the worst case? And similarly, how much loss does the best group NV-free or group equitable solution incur? And these two theorems show that in the worst case, these two objectives are indeed quite far apart. So if you simply minimize loss, in the worst case, you can be very unfair and vice versa. Of course, this is a very worst case analysis, and we wish to also explore the average case scenario, which we do in our experiments. So our goal with the experiments was to largely propose a practical training regime for fair classifiers under our definitions, and also broadly compare the loss and unfairness trade-off. Now, due to a lack of preference-based data publicly available, we largely work on synthetic data that we design for a multi-class classification setting. For our classifiers, we use a linear classifier, one versus all, as this is the classifier that we used in our generalization results, so we wish to be consistent. And our randomized classifier is simply a mixture over k-deterministic classifiers. We minimize loss while using fairness as a constraint, whether that be group NP-free or group equitable. And we derive a convex relaxation based on multi-class SVM, following the approach mentioned by Balkan et al. In their NV-free classification paper. And in our experiments, we compare ERM solution, which simply minimizes the loss, with ERM with group NV-free penalty, ERM with group inequity penalty, and ERM with social welfare reward. And this last one is basically a very simple utilitarian notion of dealing with this data, which simply attempts to maximize the utility to all individuals. So this is not part of the fairness metrics. This is simply something else to just compare results with, and it simply maximizes the utility or attempts to maximize the utility for all individuals. And lastly, we also compare our group NV-free solution to the prior work by Balkan et al., which basically designed classifiers that satisfy individual NV-free. So we wish to compare how well our relaxation works really, and what the trade-off is. So in our first result, in our first experiment, we fix the number of groups to be 4, and we apply NV-freeness or equitability between all pairs. And we sweep or move the number of training agents between, I believe, 20 to 140. So the red lines is ERM, the blue is ERM with welfare, the green line is ERM with group NV-free, and the orange line is ERM with group equitability. So some quick takeaways, we know that ERM welfare generally performs quite well in terms of the fairness metrics. So the second plot is the average group NV incurred, and this third plot is average group inequity incurred, and we wish to minimize this. So we note that ERM welfare performs quite well in these two metrics. However, this is kind of expected since it's basically attempting to give individuals what they want and giving them preferred labels. And we notice a trade-off with this when we go to the loss. So we note that ERM welfare suffers the highest loss, which is the first plot. On the other hand, ERM group NV-free and ERM group equitable provide reasonable trade-offs. So we notice a significant reduction on fairness, 50% for ERM group envy-free and 30% for ERM group equitable, without incurring a significant increase in loss, at least when compared to ERM welfare, which is, I guess, the simplest thing you can do. So our next experiment, we fix the number of agents and sweep the number of groups. And again, we notice a very similar trend. ERM welfare does very well in terms of the two fairness metrics, but also incurs the highest loss. And group envy-free and group equitable kind of find a nice satisfactory medium. So in our last result, we compare group envy-free with the individual envy-free classifiers that were proposed by Balkan et al. And we notice that individual envy-free performs quite well with respect to group envy-freeness. And again, this is not that unexpected because individual envy-freeness is indeed a much stronger condition than group envy-free. Individual envy-freeness is essentially saying that each individual should be envy-free with all possible individuals, whereas group envy-freeness is doing this in an average sense across groups. So it's kind of logical that individual envy-freeness would do well in both metrics, both of that be group envy-free in the middle plot or individual envy-free in the third plot. However, the main issue with individual envy-freeness is the high training time, which we see on the fourth graph. So the gray plot is individual envy-free and the green plot is the group envy-free. And we note that the training time simply just explodes over as the number of agents scale. And the reason for this is, again, expected because individual envy-freeness, the constraints are applied between all individual pairs. So if you have n agents, the constraints will scale quadratically with the number of agents. However, group envy-freeness, the number of constraints scale with the number of groups. So it doesn't really scale with the number of agents. And in most settings, the number of groups is far smaller than the number of individuals. So practically speaking, this makes group envy-freeness a more desirable methodology. So to conclude, fairness is a rapidly growing area of interest in machine learning, as it should be given the societal impact the machine learning is having and continues to have. We contribute to this literature by studying the applicability of two prominent economic notions of fairness in the setting, envy-freeness and equitability. We propose novel relaxations of these definitions. We call them group envy-free and group equitable for looking at fairness within groups and across sensitive attributes. And in doing so, we unify several previously proposed group-based notions of fairness under a single framework and extend them beyond the binary classification setting and into also the heterogeneous preference settings. We provide robust generalization bounds for our metrics and experimentally evaluate our proposed notions. Thank you all for listening. I really appreciate it. And thanks for joining in on our presentation. Please feel free to reach out to us with any comments or questions. The email there is my personal email, and please do read the paper. Thank you and take care and stay safe.